In this lecture, I will introduce memory resources and how the system and its processes view random access memory. In order to run any process or instance of a program on a computer system, we need to provide two critical resources: access to the CPU and access to random access memory, or RAM, for storing and manipulating data. RAM is a type of dedicated hardware memory that is attached to the motherboard. It is separate from persistent storage or hard disk space. RAM is also volatile, which means that it loses its contents whenever power is interrupted to the RAM modules, including whenever the computer is turned off. At a low level, the computer hardware presents memory to the operating system as one large block of space. This space is divided into bytes, and each byte in memory has a unique address that can be used to access it. A 32-bit architecture provides enough of these byte addresses to utilize up to 4 GB of RAM. Above that amount, there is not enough space in a 32-bit number to store the address of any memory locations in excess of 4 GB. Thus, a 64-bit architecture is required for systems with more than 4 GB of RAM. Each process, or running instance of a program, on a system uses a different view of memory. Process memory is divided into several pieces: the stack, the heap, global variables, and the text segment. The stack is used to store automatic variables, or variables that are local to functions in the C programming language. Space on the heap is manually allocated and deallocated by the programmer when writing C code using the functions malloc and free. Free space for extra data is located between the stack and the heap, and the stack and the heap grow toward one another. Global variables are provided with their own section of memory, which is allocated between the heap and text segment. The text segment is used to store program code. This segment of memory is read-only and cannot be changed. As I mentioned in the previous slide, automatic variables are placed onto the stack. This placement is performed by the compiler when the program is built. Placement of data onto the heap is historically performed by the programmer, although many of these operations are now automated in modern dynamic languages. In the C and C++ languages, the programmer must explicitly request and release, or allocate and deallocate, heap space. In C, these operations are performed using the malloc and free functions, while the new and delete operators are used in C++. In Java, the programmer must explicitly allocate space on the heap using the new keyword. However, the Java runtime automatically determines which heap allocations are no longer in use and frees those locations automatically. This process is called garbage collection. Python provides both automatic allocation and garbage collection. Whenever a data structure requires heap space, the Python interpreter allocates it automatically. Once a data structure is no longer in use by the program, the garbage collector deallocates it without programmer intervention. Use of heap memory in processes presents a challenge to the operating system because these allocations and deallocations are not known in advance. The compiler is able to track and report the amount of stack space needed, since the number of local variables in a function never changes in a language like C. However, the number of heap allocations may vary from program execution to program execution, making it impossible to know exactly how much space should be allocated in advance. Worse, heap memory allocations tend to be small and frequent, so the process of allocating memory from this section needs to be fast. This speed and dynamic availability needs to be maintained while the operating system shares the computer's RAM among multiple processes at the same time. In addition to sharing memory among processes, the kernel has memory requirements of its own. Aside from the kernel code and its own automatic variables, the kernel is filled with data structures that dynamically grow and shrink during the course of system operation. These data structures are numerous and include process control blocks, the ready list, scheduling queues, device access tables, and many other types of structure. Unlike some processes, however, all memory allocation and deallocation in the kernel is performed by the kernel programmers. In the Linux kernel, programmers can use one of a number of functions, including kmalloc, kzalloc, vmalloc, K-free, and V-free. The first issue that must be solved by the kernel is sharing memory between itself and a user space process. This sharing is accomplished first by dividing the memory into two regions, kernel memory and user memory. The kernel keeps its data structures, program code, global variables, and automatic variables in kernel memory, isolating these items from the running process. Process memory is placed in a separate region from the kernel, but the kernel is always available in memory. This mapping is necessary to maintain performance whenever an interrupt occurs, the process makes a system call to the kernel, or the process experiences a fault that must be handled by the kernel. So, how do we go about running multiple processes at the same time? Well, the first way we can consider, which is used in some types of embedded systems, is to divide the memory into fixed-size chunks called partitions. A memory partition is a single region of RAM that is provided to a single process. Both the program code and data associated with each process must fit within this pre-allocated space. If a process grows too large, it will run out of memory and crash. Furthermore, the maximum number of concurrent processes, called the degree of multiprogramming, is limited by the number of partitions available. Once all memory partitions are used, the system cannot start any new processes. This situation is exacerbated by the fact that small processes may not be using their entire partitions, resulting in wasted memory.